What we are studying right now are referred as non-ideal effects or secondary effects of BJT. Early effect along with punch-through breakdown are covered in the last lecture. Punch-through breakdown is actually extreme case of early effect. In this lecture, we will cover avalanche breakdown and non-uniform base doping. The rest topics will be covered in the next lecture. You already have a little idea about avalanche breakdown as you have studied it in PN junction also. In PN junction, dominance of breakdown mechanism depends on doping concentration. For heavily doped PN junction, Zener breakdown dominates, whereas for lightly doped PN junction, avalanche breakdown occurs prior to Zener breakdown. In BJT, however, avalanche breakdown dominates punch-through breakdown, and there is no significance of Zener breakdown, at least at normal operating conditions of BJT. We generally assume that the BJT is operating in active region, where collector junction is reverse biased and emitter junction is forward biased. Therefore, it is quite obvious that when we talk about breakdown of BJT, then we are considering the breakdown of collector junction. But if we reverse bias the emitter junction, then for that particular junction, Zener breakdown will dominate. But we will focus on BJT operating in active region only. Avalanche breakdown in itself is not destructive, but since it is an regenerative process, it eventually leads to overheating of collector, damaging the BJT. Take any random device. It can be both a PN junction as well as BJT. We will connect it with an ideal battery such that the battery is able to produce high currents without being damaged. Further, assume that this device is going through avalanche breakdown with multiplication factor say 1.31. Therefore, output current of this device will be equal to 1.31 times input current. Let's say initially input current enters the device and after some time it comes out of device being multiplied by 1.31. This output current eventually has to come back at input terminal and passing through the device it will again multiplied by 1.31. The output current further increases by a factor of 1.31 and this procedure will keep on repeating and if uncontrolled will lead to very high currents which can cause the device to overheat. There is another term, thermal runaway, which is closely related to avalanche breakdown. Even though it is a common phenomena that can happen in a variety of electrical devices, even in batteries it can happen. We will take reference of BJT. Suppose that collector current increases. It will lead to increase in power dissipation, which will result in rise of temperature within the device. And we have already studied that temperature increase leads to increase in gain parameters. And the increase in gain parameters will eventually lead to increase in collector current. So you can see this is also a regenerative process. It should be clear to you that avalanche breakdown and thermal runaway are different concepts. However, avalanche breakdown contributes to thermal runaway in BJT. Here we have two formulas which you should know. Multiplication factor for a BJT is given by 1 upon 1 minus collector base voltage divided by breakdown voltage of collector base junction when emitter is open circuited raised to the power n, where the value of n can vary from 3 to 6, which is an empirical constant depending upon semiconductor. Another formula is breakdown voltage of collector emitter diode when base is open circuited is equal to breakdown voltage of collector base diode when emitter is open circuited into nth root of 1 minus common base current gain. By simple rearrangement and approximating the value of common base current gain to be equal to 1, we can write breakdown voltage of collector emitter diode when base is open circuited to be equal to breakdown voltage of collector base diode when emitter is open circuited divided by nth root of common emitter current gain. We generally assume that the base as well as collector and emitter are uniformly doped. However, that is never the case. For PNP type BJT, we start with P-type substrate, then diffuse donor atoms to form compensated N-type base, and then we diffuse acceptor atoms to form doubly compensated P-type emitter. The approximate doping concentration profile is represented for the three regions of BJT. This non-uniform base doping results in an induced internal electric field. the balance of electron drift and diffusion currents at equilibrium requires net current density to be equal to 0. If the net donor doping concentration of the base is large enough to allow the approximation that at both the junctions base doping is equal to diffuse donor doping, then we can neglect acceptor doping concentration of the substrate. Therefore, the approximate value of electric field within the vase comes out to be equal to minus Boltzmann constant multiplied by temperature divided by magnitude of charge on an electron into donor concentration into gradient of donor concentration. After examining the direction of electric field, we can see that this induced electric field actually pushes the incoming charge carriers from emitter to collector in base. Hence, this electric field is called accelerating electric field. Most of the non-ideal effects degrades the BJT performance. However, non-uniform base doping actually improves the BJT efficiency as more charge carriers coming from emitter are pushed towards collector. You may think both early effect and non-uniform base doping lead to increase in gain parameters, but it is favorable in non-uniform base doping only. Why this is so? This is because non-uniform base doping is an inbuilt phenomena which is present in BJT from manufacturing stage and we cannot manipulate it afterwards. However, early effect is caused by external applied field which we can change and hence varying in nature even after manufacturing processes are done. These variations results in undesirability of early effect.